the talk of the today's seminar. So this is the second talk in this series of cryptography lessons in our seminar. So our speaker today is Amar Bapić, and he will talk about cryptographically significant mappings over F2 to the N. So Amar, please just go ahead.
Thank you very much. So as last time, as Nastya said, starting on these talks will be more mathematical. So since I'm the first one, I decided to give some really basic definitions of all these things that we will be talking about, so that for the future talks regarding these crypto themes, you will have a better insight of what we are talking about. So just a simple overview. So in the first part of the talk, we will be talking about these basic definitions and notions about Boolean functions, as well as the vectorial Boolean functions, define what are band functions, give some short introduction about linear cryptanalysis and differential cryptanalysis, what APN and AB functions are, and at the end, in the second part of the talk, we'll be talking of some of the current research that we have been doing regarding the duality of gold AB components. So bear with me, the first part might be a bit boring, but I will try to make it fun at least a bit. So a Boolean function is simply said any function going from the vector space, n-dimensional vector space over F2 to F2. So basically we are taking binary vectors and mapping them to 0 or 1. Boolean functions have many applications, but the primary ones would be in the design of certain cryptographic algorithms, particularly stream and block cipher algorithms. We will be more focusing on the block cipher part. So, but of course, not all are fit to be used. If you want to use a Boolean function, a certain algorithm, cryptographic algorithm, we needed to satisfy some properties. Some of them would be like balancedness, strict avalanche propagation criteria, high algebraic degree, and high nonlinearity. We will be mostly focused on the last part, so high nonlinearity. The previous three and also a bit about nonlinearity you can find in Nastya's master thesis. She has really nice sections about each of these properties, so you can get a better insight of what they represent. But we will focus mostly on high nonlinearity. So Boolean functions can be represented in many ways, depending also if we are considering the function over a vector space or in the finite field notation. So the thing is that every n-dimensional vector space F2n can be identified with the finite field F2 to the n by simply fixing a basis in the field. But for the purpose of this talk, we will consider that we are using the vector space notation. So one of the representation would be the so-called ANF, or algebraic normal form. So basically it is a polynomial of this form. So it might kind of look ugly, but an example would be, I don't know, x0, x1 plus x2 plus x1, x2, x3. So something like that. We have basically these source of these products of xi's. And of course, something that's really important would be the algebraic degree. So that would be the maximum weight of these non-zero of these u that appear in AU, where this is non-zero. So for example, if we would have x1, x0 plus x2 plus x1, x2, x3, the degree would be 3 because the largest product had 3 variables. So that's the algebraic degree of the Boolean function. So why is nonlinearity important? So it's important because it measures how, in a sense, how far away a Boolean function is from the set of all affine functions. Why is that? Well, affine functions have the lowest cryptographical complexity, so to say. They are not secure, and we don't want to be anywhere near them. So the thing is to get far away from those functions as possible. So that's how nonlinearity is defined as the minimum distance between the function we are considering and going over all affine functions. And the distance is simply we sum up the two functions and count once, and that would be the distance between f and an affine function, and the minimum one would be the nonlinearity. Of course, there's an upper bound for Boolean functions regarding nonlinearity, and it's this value. And functions that are really interesting are those that reach this bound with equality, and they are called Bent functions. And in some sense, we can say that they have the most complex structure. So functions having nonlinearity equal to this value are called Bent functions. They were discovered independently by cryptographers from the US as well as the Russians, but at the time being, those things were classified as confidential. So it wasn't until 1976 when Rothaus was allowed to publish his groundbreaking paper on these bent functions. And starting from that onward, a lot of research has been done on those functions, on their properties, their characterizations, their constructions, and so on. And a lot of research is still being done today. So there are many applications. They're used in the construction of authentication schemes, hash functions, Gerdo codes. Also, they're interesting because they're equivalent to certain Hadamard difference sets, as well as strongly regular Cayley graphs. Also, the classification problems of Hadamard matrices and bent functions are equivalent. So you can see that they have incorporated their way into other fields of mathematics. As you can see, combinatorics, group theory, graph theory, and so on. Bent functions are interesting, and that's okay. But for more interesting, also for me, would be the vectorial case. So instead of looking that an n-bit input is outputted in 0 or 1, we also consider to have an m-bit output, and that's what basically vectorial Boolean functions are. So mappings from the vector space f to n to f to m. Also, they are called s-boxes, which we'll later on talk about in another sense, as well as nm functions. And they can be expressed in this form. Each of these small f1 to fm are Boolean functions, and they are called the coordinate functions of capital F. And for every non-zero vector in f2dm, we can define this function, which is basically the linear combination of the coordinates, and this is called the component function. So since we are in f2 to the m, there are 2 to the m minus 1 component functions for a vectorial Boolean function. And as well, we can talk about the algebraic degree. So the algebraic degree of f would be defined as the maximum degree of the components. Also, an important thing which we will later on use would be the Walsh-Hadamard transform. So if we have an nm function, we have this mapping going from f to n times f to m to z, and it's defined in this way. And this is called the Walsh-Hadamard transform of f. This value here are called Walsh coefficients, and the multiset of all Walsh coefficients is called the Walsh spectrum of f. In the second part of the talk, we will be using this a bit and talking about more. So vectorial Boolean functions, or in this sense, we will refer to them as S-boxes, are parts of iterative block ciphers. So how to explain block ciphers? So basically, you have a plain text, which you divide into parts called blocks. And each block is then encrypted using some round key. So in block ciphers, you have many rounds, and each key in each round we use a key called a round key, and also in each round we have a function called round function. So the round key is basically computed from one main master key using some key scheduling algorithm. Later on, you will see a picture of a block cipher of the whole system, so you will get a better visual representation of what is going on. For example, two notable examples of such S-boxes are not S-boxes, of block ciphers. This is a typo. Are DES and AES, so the data encryption standard and advanced encryption standard. So one iterative block cipher would be the so-called substitution permutation network. So what we have, we input the plain text, which is then feeded into these S boxes. So this is called the substitution stage. And in these in this part here, we are mixing the key bits with those of the plain text in a nonlinear way. And this is called the Shannon's property of confusion. And after that, we have a permutation stage. So basically, we are trying to remove all the redundancies by permuting the bits that were outputted by these S boxes and then feeding them into the next X box. So that is called Shannon's principle of diffusion. And it was Shannon, even if you Google this, you can find it also on Wikipedia. For a block cipher or to be safe, you have to satisfy these properties of confusion and diffusion. And we will be mostly interested in these S boxes. So, well, okay, we know what a block cipher is, but also important would be how to construct block ciphers. Okay, what would be a smart way to do so? There are many attacks on block ciphers. Two are really notable, which are called the linear differential attack. And in order to resist those attacks, you have the criteria for the resistance of those attacks has also implied the criteria for the design of these block ciphers. So firstly, we'll talk about the linear attack and see how a block cipher has to be constructed to resist the linear attack, and then we will talk a bit about the differential attack. So the linear attack was introduced by Matsui in 1995. So it is the idea is to find a probabilistic linear relationship between a subset of plain text bits and subset of state bits preceding the last round of the substitution stage. Basically, the idea is to find a subset of bits whose XOR behaves in a non-random fashion. And it is also a non-plain text attack. So the attacker we assume that the attacker has a large database of plain text ciphertext pairs, which he can use to try to attack or essentially break the cipher. So before we get to the attack, we will have to recall some things from probability theory. So suppose that these capital X1, X2, and so on are independent random values. And with small p1, p2, and so on, we will define the probabilities that random values are 0. Well, in that case, we know the probability that it's 1 is 1 minus pi. So if we suppose that I and j are not the same, the probability that we have, so that xi is equal to a and xj is equal to b, where a and b are 0 or 1, are these probabilities here, which are really easy to see. From this, it is then easy to compute what the probability of the XOR of xi and xj is. So it will be this one, and these two formulas will be used later on. You will see why. So because we are talking about because our values are only 0 or 1, it is more convenient to define another quantity, which is called the bias. So it is defined as the probability minus 1/2. Why? Because somehow if we have an optimal situation where everything is random, then the probability of us knowing if a random value is 0 or 1 would be 1/2. So we are kind of trying to see if we can move a bit away from that 1/2. So that's why we define the bias. Then it is easy to see that the bias, the probability of the previous slide can be represented in this way. So epsilon I plus minus 1/2. And because we will be considering XORs of certain random values, we are interested in what the bias of that random variable is. So if we denote with epsilon this I1 going to ik denotes the bias of this random variable, then it can be computed as 2 to k minus 1 times the product of all these biases of each of the independent random variables. Of course, it's important to mention that the variables have to be independent, otherwise this lemma doesn't hold. So to show the attack, we'll consider an example to see what is going on. So for example, we will consider an Xbox, which is a permutation. It doesn't necessarily have to be a permutation. The input and output space doesn't have to be the same. So maybe it's just for easier references, we assume that in this case we have a permutation, so which is defined with this table here in hexadecimal notation. With capital X, we will define the input, and with capital Y, we will define the output. And we have a table that records all the possible random variables depending on the S-box. So basically, as you can see here, we have the vector space F2D4, and then here we have where they are mapped. And we will be using this table to see some relationships. So for example, if we would consider the XOR of the variables x1, x4, and y2, it is easy to compute that the probability that this variable here is 0 is 1/2. How do we do that? Well, we just sum up this, we compute this, count how many times we got 0, and divide it by 16, the size of the number of rows. And we got 1/2. So this means also the probability that it's equal to 1 is also 1/2. So the bias is equal to 0. Well, we don't want that because a linear attack can be potentially mounted if the random variable has a bias that is bounded away from 0. So this is not really useful. But if we consider another variable, for example, t, defined in this way, then we obtain that the probability that t is equal to 0 is 1/8. And in that case, the bias is -3/8, which is really good for measuring non-uniformity. So the bias is away from 0, which means that this we could potentially use to mount an attack. But this was just for one variable. We have to do this for all possible random variables. And that's why we have to find them in this form as this sum, where xi is connected with these ai's and yi is connected with these bi. And the vector A is called, consisting of these, is called the input sum because x is input, and B is called the output sum. And we define the following quantity. So if we have a random variable with input sum A and output sum B, for all 8 tuples of this form, satisfying this, of course, we want the output to be the image of the input, and as well we want this quantity to be 0. In that case, the bias of the random variable is equal to this. So the number of NL of AB minus 8 divided by 16. And we will do this for all possible AB, and we will get a large table, which I have not put because it would be too messy. This table is called the linear approximation table, or LAT. And from that table, we can see which random variables consisting of XOR of xi and yi are nice to use for the attack. So where we have to look where the bias is moved away from 0. So and we take those variables and then do something with them. For example, for that permutation, we have these 4 S boxes, which are colored blue. And for each of them, we have these random variables. So as you can see, for example, for S21, we have here U5, U7, and U8 in the first round. So the upper index is the round of the cipher. And as well, we see that the output is V2. So this is one random variable, and it is computed that it has bias 1/4. And we do the same for these other 3 S boxes. And because T1, T2, T4 are independent variables, using the piling up lemma, we can see that the XOR of them has bias equal to -1/32. So we are again away from 0. So this means that we can possibly mount an attack. Now, the idea, furthermore, after some ugly calculations, when you consider the XOR of these four variables, you get that it's equal to this. So x5 plus x7 plus x8, which are the inputs. These are some some inputs in the fourth round of the key, and we have some key bits. Now, why didn't I write out the key bits? Well, supposing that the key bits are fixed, this is either 0 or 1, so we can kind of forget about it. So basically, we are left with just this random variable, and we know that it has a bias equal to plus minus 1/32. Okay, so this is nice. We have something connecting the input bits and the state bits. We have a bias away from 0. So what do we next? We know that it's a known plaintext attack. So assume that we have T plaintext ciphertext pairs, which use the same unknown key K, which we want to find. The idea is we can, when we consider this input variable, and when you just follow the arrows, you can see that they end up in these S boxes here. So the index should be up, sorry. So S42 and S44. And for these two S boxes, we have here 4 key bits, and here also 4 key bits. So the idea is to kind of try to find what these key bits are. So this would be a partial result. So how do we do that? For each pair XY of known ciphertext, plaintext, for each ciphertext, we can do a partial decryption, and we can find what these values here are. So basically, we can find U4-6, U4-8, U4-14, and U4-16. So we can find this part here for a certain ciphertext. And for the plaintext, we use these bits here. We compute those, and we want to have 0. And we do those for all possible keys. So since we have 8 bits, we have 2 to the 8 computations. And each time we get a 0, we kind of increase a certain counter. Now, the idea is if we have T plaintext ciphertext pairs, the idea is that approximately T half would correspond to each other. More precisely, because we have a bias plus minus 1/32, the number of zeros we would obtain for a certain key for a certain 8 key bits, or for in that case it's called a candidate key, would be T half plus minus T/32. And the idea is the key that has that number of the counter corresponding to that key has that number, it will be high probably the key bit which is used, and in that case we would obtain 8 bits of the key. And more or less that would be the idea of the attack. So sorry if it was a bit too rushed. Also, if you go on YouTube, there are really 2 nice videos about the linear and differential attack. It is explained nicely. They're a bit long, but you will get a really nice and clear picture of what is going on. Also, you can find more details on this in the book of Stinson's on cryptography. Okay. So what was the problem here? Why could we do this? Well, as said at the beginning, we are trying to find a linear relationship between some certain bits. Well, how do we do that? Don't have linearity. So that's why we want the block cipher to have high nonlinearity. That's why it's called linear attack. If there is a high nonlinearity of the S box that is used, then there won't be probably a way for us to find a linear relationship between the bits, because we don't have any linear relations. So if you have high nonlinearity, then you are safe, at least for linear cryptanalysis. Well, on the other hand, also another popular attack, also to mention, for example, DES. It was That can be broken in many ways, but if it is attacked with linear cryptanalysis, excuse me?
Can you hear me?
Yes.
So what is your statement that the desk can be broken in many ways?
Well, I read that there's like you can attack with brute force, you can use linear cryptanalysis, you can use differential cryptanalysis, depending on the time. But for example, if you use linear cryptanalysis on DES, then you would need approximately 2 to the 43 plain text ciphertext pairs, which is better than going over the 2 to the 54 all possible key bits. If you're using differential cryptanalysis, then you would need 2 to the 47 plain text ciphertext pairs. That's what I read.
Yeah, okay, and that's feasible for you or what?
No, I mean,
well,
for me,
yeah,
not.
yeah. So, well, be careful about broken in many ways.
Yeah, okay, I understand.
Yeah.
Yes. It's better than the going over all the possible keys, but not feasible. Yes, I agree.
Yeah.
Okay, differential attack, I will just mention it because we're running out of time. So it was introduced by Biham Samir in 1990. Basically, the idea here is to consider the differences between some inputs and outputs. So basically, if we have a C and C prime to be ciphertexts, we consider their XOR, and we consider some plaintext M and M plus alpha and some probabilities. I will not go into detail here. The idea is just how to avoid it. So the resistance criteria would be if the derivatives, which are defined in this way, are as uniformly distributed as possible. We will later on talk about this a bit more. Again, encourage you to go on YouTube and look a really nice video about the differential attack also, where it's explained with examples, so you can get a really nice idea of what is going on. Well, again, as we said, we want high nonlinearity in Boolean functions. We know that bent functions have the highest nonlinearity. Okay, we are in vectorial case, so there should be probably vectorial bent functions, and there are. So the nonlinearity of a vectorial function is defined as the minimum nonlinearity of its components. So basically, you always end up in a Boolean, considering the Boolean functions. Almost all properties of vectorial Boolean functions are defined over its components. Also, the universal bound holds as well in this case. So we have that the nonlinearity is upper bounded by this value. And of course, the functions achieving this bound then are called vectorial bent functions. Another way to define them, we would say that the NM function is bent if and only if all of its components are bent. So that is nice, but there is a small drawback. As was shown by Nienberg in 1995, vectorial bent functions exist only for m less or equal than n half, which is not good. Why? Because mostly when you use when you consider block ciphers, you want it to be reversible. You want to have an inverse, but to do that, you want the input and output space to be the same. So the question is, what to do when m equals n? What functions to use then? Well, in case of odd dimension, the nn function that have highest nonlinearity are called almost bent. But in the case of even dimension, upper bound on nonlinearity is yet to be determined. So to find the optimal value of these functions. So for odd dimensions, we know what they are. For even dimensions, it is still yet to be determined. But how do we define them? So the nn function f is said to be almost bent if and only if the Walsh spectra has these values, so 0 and plus minus 2 over n plus 1/2. We will be talking about one AB function at the end of the talk, namely the gold function. So another function, type of function that's really interesting and important are called APN functions, or almost perfect nonlinear functions. So assume that we have an nn function f, and we define the difference spectrum or difference distribution table as a multiset of these values, delta f, a, b, where a is non-zero. Basically, what are these delta f? This is actually the number of solutions of this equation, where this is the derivative which we defined before. And the maximum value in the DDT is called the differential uniformity. We say that f is almost perfect nonlinear if the differential uniformity is 2. So as I mentioned before in the differential attack, we said that we want the derivatives to be as uniformly distributed as possible, and it is proven that this is done if the differential uniformity is equal to 2. So APN functions offer resistance against differential attack. Also, because of this, we refer to APN function as differentially 2 uniform functions. So here I've chosen to show you this table of known APN, AB, sorry, typo again, AB and APN power mappings. So these are the known ones: Gold, Kasami, Welch, Niho, Inverse, and Dobertin. We will be talking about this Gold function, which is a quadratic AB function if n is odd. And it's basically defined as x to 2i plus 1. Here we see that we are talking about in a finite field notation. And also I would maybe point out the inverse function, which is used in AS as the S box. So the inverse function is used there. It is has high nonlinearity, offers a resistance against the differential and linear attack.
Maybe you should say here that degree is the Hamming weight of exponent, right?
Yes. Yes, because it's finite field notation. Yes, I agree. So yes, the algebraic degree is the weight of the exponent. So that's why it's n minus 1. Okay. And Dobertin conjectured that the list of APN power functions is complete. So this is yet to be determined. Okay. Well, as mentioned before, we again said that we want our S boxes to be invertible, so we want them to be permutations. So the thing is, when considering APN, okay, let's focus for power functions. So the table before, they are permutations if n is odd, and 3 to the 1 if n is even. Thus, in the case of odd dimension, we know that APN permutations exist. Okay. Now the question is, what about APN permutations in even dimension? Well, the problem, pretty big problem here. Computationally, it has been shown that for n equals 2 and 4, there are no APN permutations. In 2009, Dillon gave the first and up to date only example of an APN permutation for n equals to 6. For n equals n greater or equal than 8, the question still remains open. So there has no function yet to be, there hasn't been an APN permutation found in these dimensions. And that's why we have this big APN problem, which basically is, do we have an APN permutation in if n is greater or equal than 8 and even? Professor Charpin and Professor Enes also told me that they do not believe in the existence of APN permutations for n equals 8 because, quote, the structure of f2 to the 8 is weird. So a lot of research is still being done on this field on trying to find APN permutations in even dimension. And so we are still waiting for either a yes or no answer. Does it exist or not? Okay, so basically that would be an overview of all these different functions that we are researching about: bent, AB, APN, vectorial case, Boolean case, and so on. So now I want to talk a bit about our current research. So this is together with Samir and Professor Enes. So what we do, we consider the components of the Gold AB function, where n is odd, of course. Then for every non-zero, then we know that every component is a quadratic semi-bent Boolean function. Okay, this semi-bent is new. So basically we say this Boolean function is semi-bent if and only if the Walsh coefficients are 0 or plus minus 2 to the n plus 1/2, which is true because that's what basically AB functions are. They only have these values in their Walsh spectra. Also, what we will need is something called the Walsh support of the components, coordinates, either way. In this case, let's say SI. Those are basically all the vectors in which the Walsh was not 0, and that is the Walsh support. And also, because we know that it's a semi-bent, we will define some function fi star going from the support to f2 in this way. So why? Because we know that on SI, we know that the Walsh is plus minus 2 to the n plus 1 half. So basically, it's 2 to the n plus 1 times minus 1 to the something. It's either 0 or 1. And this function here determines the sign. So to note some things, so if we have a quadratic semi-bent function, then we know that the supports are affine hyperplanes, so n-1 dimensional affine subspaces. So this means that they can be represented in this form, z plus e, where z is a vector in the support and e is a lexicographically ordered n-1 dimensional linear subspace. So what do I mean with lexicographically ordered? It means that if you consider the integer representation of vectors, it has to be ordered in a way. For example, if we have this support here, we can define it as 0, 1, 0 plus these vectors. And of course, we can see that this is lexicographically ordered because this is 0, this is 1, this is, what is this? 1, 2, 6, and this is 7. So we can see that this is ordered from smallest to largest. And the nice thing here is that we can make a direct correspondence between the support and the finite field, the vectors n-1 dimensional vector space over F2 through this E as follows. So we know that this Fi star of omega j is defined of the support. Furthermore, because it is in the support, we can write this at z plus ej. Ej is in E, which is ordered lexicographically. So if we assume that the vector space is also ordered lexicographically, we can say that this equals to some Fe star overline of xj. And in this way, so using this equation 2 and this equation 1, we can define something that is called a dual of Fi. And these duals are pretty nice for quadratic semi-bent functions. Why? Because since SC is an affine hyperplane, we know that these duals are bent on F2 to the n-1. So going from an n-dimensional space where it was semi-bent, we can define its dual on a space 1 dimension smaller, and on that space, that function is bent. Furthermore, because all the components of the Gold function are semi-bent, we know that Fi plus Fj is also quadratic semi-bent. Well, but that means then that the dual of that function is bent on F2 n-1. Well, what can we then say about the bentness of this function? So if I take Fi, define its dual, and Fj, define its dual, what can I say about the bentness of their sum? Okay, we will shortly note this with Fij star line. Well, in general, it doesn't have to be an equivalent statement. So the bentness of this is not necessarily imply the bentness of this. Well, for that purpose, suppose that we are given two Walsh spectra corresponding to these duals. And we have defined the following two mappings. So Pij and Pij inverse. So basically, we have the Walsh support of one, the Walsh support of the other. And we have 2 to the n-1 half. You will see why it is defined this way. And the inverse is defined in this way. Also, I don't want to go in detail how we obtain that, but let's say we have these two mappings defined. Let's see at some values. For example, if I take the Gold function x to the 5 defined on the F2 5, and I have computed the products, which are these values here. So if you can look at here, we have 8, 8, minus 8. So somehow this looks as a Walsh spectra of a bent function. Why? Because in this case, n-1 is 4. So we have plus minus 2 to the we have plus, sorry, not bent spectra. That was a sorry, I'm a bit foggy. Typo in lapsus. So we have these values here. The thing is, what does this tell us? So if I do the inverse, because the inverse is defined with these Pij, for this table here, I obtained another table, this one. And now, if you look at this one, there are some things that kind of stand out. What would it be? Well, if you consider these three rows, you can see that these vectors here are all plus minus 1, which was interesting when I obtained this computationally. And then when I looked into a bit further, what did I obtain? I obtained that fi star plus fj star was actually bent in the cases where this was plus minus 1, which initially then gave a characterization for the bentness of the sum, for summarizing this theorem. So if we have k quadratic semi-bent functions, we have then their corresponding duals, then we know that their sum is bent if and only if the inverse was 1, P inverse was 1 for all vectors u in f to the n minus 1. Well, characterizations are nice to have. They tell us what is going on, but it is not as nice to have an actual design on how do I construct functions that will have these properties. So it does give us nice characterizations, but it doesn't give us an efficient construction method. And that is what we're mostly considering now. So some of the problems that we are looking in, if I have how to choose or construct a Walsh support SI, and then the corresponding functions fi star to obtain a quadratic AB function, or more, so if I have fi star plus fj star bent, how can I generalize it to maybe 3 functions, 4 functions, to have a sum of multiple functions to be bent? And otherwise, can I construct a vectorial bent function? So I know if I have fi star and fi, for example, f1, f2 to be bent, f1, f3 to bend, all their sums are bent, then I know that f1, f2, f3 is a bent vectorial function. So how can I plug out the components or coordinates to obtain a bent vectorial function computationally for the gold case? It is there; they do exist. If you consider the coordinates or even components, you can plug out a subset of these functions such that they form a vectorial bent function. But why and how, that is still yet to be determined, and that's what among the things that we are currently looking at. And also another question that popped out is, if I have a quadratic semi-bent function f, how can I find another semi-bent function g so that f plus g is again semi-bent? If it has been during the writing of this article, it has been extremely difficult, even for the quadratic case. There have been so many propositions and things that have to be satisfied. The notation was so complex, and it's kind of weird. And also Professor Enes pointed out many times that it's the quadratic case. It should be the simplest one, but to have such a complex structure, it does kind of seem weird. So even if you manage to do it for 2 functions, how do you generalize it then for 3 functions, 4 functions, and so on? Because if you would know how to do it for multiple functions, then there is possibly a way on how to construct AB functions. And that would be really nice to have an efficient construction method for these functions that are used in so many algorithms and that are really important for practical use. So among some of the things, I maybe wanted to show some remarks that we noted when considering the intersection of these supports of the gold components. So for example, again, we will consider the gold function x to the 5th and their corresponding Walsh supports. What has been shown is that if I take any 2, 3, 4, or the intersection of all supports, I obtain these really nice values of the cardinality. So if I intersect any 2 supports, I get that they have 8 vectors in common. If I intersect any 3, I get 4, and so on. And this has been shown for dimensions 5, 7, 9, probably even for more. But still, why does this hold? That's still an open problem that I'm currently working on. More visually, if you would see the next picture. For example, here I have a Venn diagram that represents these intersections. And these numbers basically are the numbers that are in common. And as you can see, we have a really nice uniformal distribution of these vectors. I mean, almost everywhere we have only one vector in common between these parts, except for these few slots where we have a 2. But still, I'll obtain this picture, a similar picture for other functions, for other gold functions. So it is there are still some things that have to be done here. I mean, it is not a coincidence that this is happening. There is some structure probably hiding behind it, but finding these structures is a bit tricky. But also, this would be something new because because considering these constructions and these properties in this so-called spectral domain is something new. No one has done this before, so this is really interesting, and we are currently working on this. I also wanted to maybe talk about another article I was working on, but I don't have enough time, so probably I will leave that for another time, which is considering the construction, a generic construction of certain vectorial bent functions. So maybe in the next semester or so, I will talk about that. So yes, that would be.
May I comment on this picture immediately?
Yes.
So I think there is something wrong. I mean, well, this green stuff here does not contain number 2 anywhere, right?
Yes, I checked it a few times. Basically, really? Yes, that's why it's so weird for me. Also, I computed all the Walsh supports for each of the coordinates.
Yeah.
Sorted them lexicographically, so I had these nice sets of values, plugged them into a software, and which does basically basically draws a Venn diagram for that, and this was what came out. Okay,
but you were also surprised actually.
Yes.
Missing.
Exactly.
Yeah,
but all 3 have these. Although we have 1, 1 here, but we have. Okay, only the green. Yes, only the green doesn't have a 2 because we have a 2,
exactly.
2, 2.
Yeah.
So
yeah,
yes.
but there is a single 0 as well appearing.
Yes, here.
Yes, exactly. Yeah. Okay. Wow, that's really weird.
Okay, so yes, that would be it.
Okay, thank you, Amar, for the really nice talk. So are there any further questions or comments or suggestions?
I would like to ask something.
Yes.
Okay.
First, I would say thank you for the nice presentation. And I have one question. You at the beginning, you were saying something about that some functions can be represented with Cayley graphs. Does this kind of representation holds for gold functions or something like that?
No, bent functions correspond to strongly regular Cayley graphs. So they are defined if you take for the vertices, you take the whole vector space, and for the edges, you take those vectors in which f of u plus v was 1. So in that way, you can construct a Cayley graph. For every Boolean function, you can construct a Cayley graph. But in the case of bent functions, they are also strongly regular. So Cayley graphs are connected with Boolean functions.
So you cannot use them here.
Well, not that I know of. That I didn't. Probably it would be maybe some multigraph or something because we are in a vectorial case.
Multigraph. It's just that you don't have this strongly regular Cayley graphs if it's not bent, right?
Yes, but can we construct Cayley graphs for in the vectorial case? That's what's the question. If we have vectorial functions, that seems somehow unlikely. Because because we only have outputs 0 and 1, and the Cayley graphs are constructed if the value was 1, if f of u plus v was 1. But here in the vectorial case, as in gold functions, the outputs are vectors, and you have 2 to the m vectors. So it would be a bit tricky to.
Yeah, I got your point. Yeah.
That's a one-way trip, isn't it? And so a bent function gives you a strongly regular Cayley graph, but if you have a strongly regular Cayley graph,
it's an if and only if. It's a characterization.
okay.
So also every strongly regular Cayley graph corresponds to a bent function.
Well, if the group is the right one, so the group of the Cayley graph.
Yes. Okay, I agree. Yes,
the
yes.
additive group of the Z2 to the N, because
Exactly.
Cayley graphs over, I don't know, dihedral groups, for example, and they are also strongly regular, but I guess those will not correspond to
No.
this function.
Yes, I agree.
If I may, there are some additional conditions on the parameters of strongly regular graphs. So there is characterization, but with
yes,
some additional.
And they are exactly. They are also the parameters are explicitly given for the strongly regular Cayley graph, and I have it in front of me, luckily. So let me just read it out. Okay, because I was doing a bit research on this also. So E is equal to P. I just have to look at these. It says here that a Boolean function f defined on the vector space n, f to n, is bent if and only if its associated Cayley graph is a strongly regular graph with the additional property that E equals to D. Now I just have to, I don't remember what E and D are actually about.
I think these are the support of the Boolean function, the values where you have 1, right?
I think I have to, I really don't know. I mean, I know that I've read in some paper somewhere, I have read the exact parameters, and I know that it's a really nice structure, that this has a lot of these 2 to the n, but I don't know at the moment the exact ones, but I can look it up and send it to you by email if you want.
There is a paper by Edwin van Dam and Dima van der Vlas from 2003 in European Journal of Combinatorics, where they discuss these graphs coming from nonlinear functions. So maybe.
And I think that you were a reviewer of that paper, Shevko, right?
I think so. That's why I remember this paper. So,
yeah.
I
remember them mentioning. I know that paper. Yeah, you're right.
But I guess there are other papers as well, I would say. I just remember that one. So
yeah, you can introduce other kind of associated graphs with these particular kind of class of functions, AB functions, and I think that was the topic of that paper, right?
Yeah.
And deriving some combinatorial results with these set of solutions of equations and whatever.
Yeah.
Okay, I have found the parameters. So we have vk lambda mu, the standard parameters of strongly regular graph. And in the case of bent functions, we have that these are 4 to the m. Then we have something that looks like the bent distance. So 2 to the n minus 1 minus 2 to the n half minus 1, which is not a surprise.
Again, yeah, that's the support, what I told you.
Yes, and then the other two are also 2 to the n minus 2 minus 2 to the n minus 1. So the they are really, really similar, just differencing. There is one -1 in the exponent. But yeah, it's a paper by Paul Leopardi. It's classifying bent functions by the Cayley graphs. So it's really, it seems, oh, well, it's 69 pages. So I think it's an in-depth article on that.
Well, maybe you should mention as well that bent functions correspond to different sets, right? And they are
yes,
used
I mentioned to certain
theory, right? And these are the parameters of different set. Actually.
Yes, exactly.
Wow.
Okay. Any other questions or comments? Well, if no, then let's thank Amar once again. Amar, thank you.
You're welcome. Thank you very much.
For your talk, and see you all next week when we have the third lecture from this series of cryptographic lectures at our research seminar. Bye.
Okay, bye. Thank you.
Bye.
Bye, guys.
Bye, everyone.
Bye.